Hi everyone. In this video we are going to talk about infinitude of primes. Um, so we know that there are infinitely many primes, right? The basic proof is given by Euclid, right? But in this video we are also going to study another proof which uses group theory. A particular theorem in group theory, maybe we can say a basic theorem, a Lagrange's theorem on finite groups. Okay, so before that we are going to illustrate what Euclid has done, right? Yeah, so the theorem is there are infinitely many primes. You know that prime numbers are is something very special in natural numbers. You know that the prime numbers have only two factors, p and 1, right? The prime itself and the number 1, right? So in order to prove this fact, we are actually having two assumptions. First one is natural numbers are unbounded. That means you know that it's very clear 1 2 3 4 5 6, you can keep on counting and you can see that this is a this is not going to end, right? And secondly we can see another that has a nice proof also. Every natural number has a prime divisor, right? So which is greater than or equal to 2, you can have a prime divisor, right? So these two assumptions in our hand, then we are able to prove that the set of our primes are basically unbounded or infinite. Okay, so first thing is a Euclid's proof. So in Euclid's proof we assume that the script p is finite, and we also list those prime numbers p1 p2 p3 and pn, right? The n prime numbers, and we are considering a particular number, that is n. So n is equal to the product of n primes plus 1, right? p1 times p2 times p3 times up to pn and plus 1, right? And of course we use the second assumption, every natural number has a prime divisor. So by assumption n has a prime divisor, let us assume that it is p, right? Yeah, now our claim is p is not belongs to this finite set, right? Yeah, so if so I am assume the contrary. Suppose p belongs to that finite set, what happens is p divides n minus 1. What is n minus 1? N minus 1 is nothing but the product of n primes, right? Because n is product of n primes plus 1. So if you take minus 1, then you get the product of p1 p2 p3 pn, and you assumes this p is one of them. So definitely p divides n minus 1, right? Also our assumption p divides n, and you know by basic divisibility, the difference of these numbers should be divisible by p. So p divides n minus 1, that means p divides n minus n plus 1. If you cancel, p divides 1. That means p divides 1. That is impossible because p is a prime number, not 1. So that is a contradiction. That means my claim is true, that is p does not belongs to p. That means we got another prime outside p. That means p is not finite. This implies p is not finite. So this is the basic proof given by Euclid, and after that there is many proofs came out, and in my next lectures I will be doing more proofs, another 4 proofs we are going to exercise other than this. So this one is next one is coming like a proof from group theory, right? A proof from group theory. So for in this case we use Lagrange's theorem on finite groups, right? So let us just look at what does this mean. So let G be a finite group, and that means a group having finite number of elements. If you don't know what is a group is, you can visit some books or Google, you can find what is the meaning of structure group. Okay, so if let G be a finite group and H be a subgroup, right, then I denote using these vertical bars. It's a cardinality of that subgroup. So the cardinality or number of elements in H divides the number of elements in G, or cardinality of G. So this is our theorem. When H is a subgroup of G, then the cardinality of H divides cardinality of G, or we can say order of H divides order of G. Anyway, you can say. So we can have a nice corollary from this. If A is an element of G, then order of A divides the cardinality of G. How do we prove that? So let us assume order of A is M, right? So that means by this notation, let us consider the cyclic group generated by A, right? If the cyclic group generated by A starts from 1 A power 1 A power 2 like that, and that has order M, right? And a cyclic subgroup generated by A is of course a subgroup of G, right? So the number of elements should divide G using Lagrange's theorem. That means M should divide G. That means order of A should divide cardinality of G, right? So just an a corollary. This is what we are going to use. Okay, so if A is an element of G, then order of A divides order of cardinality of G. Now suppose P is finite, and we are coming to the proof. Suppose P is finite and P is small p is a maximum prime, right? Yeah. Now consider the number 2 power p minus 1. So we are considering this particular number 2 power p minus 1, and our claim is any prime factor q of 2 power p minus 1 is bigger than p, right? So definitely 2 power p minus 1 is a natural number, right? And our claim is any prime factor q of 2 power p minus 1 is bigger than p. If you prove that, what is the problem? You know, you have already said p is the maximum prime, and you are getting something out of that. So that proves infinitude of primes, right? So let's see how it happens. So let q divides 2 power p minus 1. That implies what? 2 power p is congruent to 1 modulo q. If you are familiar with the congruence relation, this can be rewritten like that: 2 power p congruent to 1 mod q, and I denote it as a hash. Okay, an equation number hash, right? Now let us consider ZQ. You know, if you know the group theory very well, ZQ is a what you can say, it's a field, right? So it's a field. So ZQ difference 0 will be a multiplicative group, right, in that field. So where this contains q minus 1 elements, because ZQ contains q elements. So this contains because 0 is avoided, so this multiplicative group contains q minus 1 elements. So the field is ZQ, right? It's a multiplicative group of field ZQ. Then by hash, what happens is 2 power p is congruent to 1 mod q. That means when you power p, right, when 2 power p is 1, that means the order of 2 is p in modulo q, right? You are getting the multiplicative identity, right? When you raise the power p of 2, you are getting 1. That means the element 2 has order p, right, in ZQ difference 0, right? Yeah. That means what? That means p has to divide q minus 1. Why? Because 2 is an element of ZQ, difference 0, and we have already studied by Lagrange's theorem, order of an element should divide order of G. So the order of element is P. It should divide the number of elements in this group, which is q minus 1. So P divides q minus 1. That means P is less than or equal to q minus 1, which is less than q. So definitely from this inequality you can see that q is greater than p. So any factor q of this number is greater than p. That means you are getting q out of the finite set, or it contradicts the maximality of p. That means p cannot be finite, right? So this is using group theory, and we may have other for proofs are also very interesting, and we will see in other videos these 6 proofs. So we have already completed 2, we will 4 about to come. So you can ask any doubts in your comments, right? Yeah, so you can message me or anything, you can clarify your doubts. Okay, so thank you for your attention. Yeah, thank you.